Hello everyone, welcome to Imaginary Hub and welcome to another lecture of linear algebra, which is SVD, singular value decomposition. In our previous classes, we have seen most of the concepts of linear algebra like elimination methods, transformations, vector spaces, null spaces, and along with it, we have seen a special type of vectors which occurs when we do transformations. Whenever we are performing different types of transformation, there is a special type of vectors for which the directions will not change. Even like they might get compressed or expanded, it doesn't matter, but the directions of those vectors will never change after the transformation as well. And we call this special types of vectors as eigenvectors. And the amount by which they have stretched or compressed is known as eigenvalues. And from eigenvectors and eigenvalues, we have built a machine learning algorithm called as principal component analysis, and from which we have extracted different patterns from n dimensional data. But if you see, there is a, you can say, some problems with PCA, and to tackle this problem we have built a new algorithm, or you can say new method, which is called as singular value decomposition. And using this mathematical concept you can extract n-dimensional patterns from the given data. So we will talk about what is SVD, how do we visualize it, and this lecture is divided into two parts. In the first part, we will talk completely mathematical concept. We'll talk complete theory, right? What is SVD? How do we imagine it? Why is that? And what is the use of that? And why it is a better approach when compared to PCA. And in the second part, we will code this algorithm. We will code this machine learning method. And let me tell you this, by this lecture, we will complete linear algebra. And by in our next upcoming lectures, we will start calculus. And the first and foremost topic which we are going to study in calculus is backpropagation and eliminations. So we will see that. But for now, enjoy the SPD lecture, and I will see you in the lecture. I hope you have learned, you will learn new things and new concepts. So with that being said, see you in the lecture. In previous classes, we have studied about different concepts of linear algebra, like what is vector, how do we imagine a vector, difference between mathematical concepts of vector, physics in terms of physics and computer science, the meanings of vectors and all. Then we went into elimination. In elimination, we have seen different concepts like Gaussian elimination, Gauss-Jordan method, matrix-based eliminations, and all sort of things. Then we went into transformations, transpose, symmetry, all these different concepts. And in our previous class, we have talked about eigenvalues, eigenvectors, and from eigenvalues and eigenvectors, we went and implemented a algorithm called as principal component analysis, which is used to reduce n-dimensional data into maximum 2 or 3 dimension and extract useful information, useful patterns from the given n-dimensional data. Okay, now in today's class, what we are going to do is we are going to study a new concept, and the name of the concept is SVD. The full form here is singular value decomposition. Okay, I hope I'm not writing it wrong. Yeah, composition. Okay, there might be some spelling mistakes. Forgive me, spelling mistakes does not matter. What matters is how well we are understanding the concept. I will divide this lecture into two parts. The first part is going to be complete theory. We are going to understand what is the intuition, how do we come up with this, what is this, why is the need of studying SVD and all, and then we will implement a recommendation system, a YouTube or Netflix recommendation, a very simple recommendation system will code SVD. Okay, now let's start with our lecture. So to study SVD, first of all, we need to understand what is the meaning of it. What is the meaning of SVD? Okay, to understand this, let's go from the basic. If you take a matrix is a rectangular grid. A matrix is a rectangular grid uh, in which we will have rows and columns. Rows and columns. And think of it as a spreadsheet, right? In spreadsheet, what we do, we store numbers in each and every cell, and each row represents something, each column represents some sort of thing. So here I can take example, let's say I'm representing Netflix movie rating, right? Netflix movie rating. Here the rows can be users, right? And movies are columns, right? So if I have to draw this matrix, then I can write my matrix as, I want you to take notes along with it. First of all, we are trying to understand what is the meaning of SVD. Then we will see why do we need it, and we'll go into numericals, okay? So if I have to draw a matrix for Netflix, here I can draw like 8, 7, 6, 9, 10, 5, 3, 8, 9, right? This is a square matrix. It can be a rectangular one as well, right? It can be like 1, 2, 3. That's it. Here the rows represent user 1, user 2, user 3, and columns represents movies, movie 1, movie 2, and movie 3, and each cell represent the rating given by user for that particular movie. If I talk about 8, 8 is the rating given by user 1 to movie 1, right? And 9 is the rating given by user 3 for movie 3. Okay, so here each cell is representing the rating, and columns are representing movies, rows are representing individual users. Okay, got it. So this is the meaning of a matrix. Matrix is nothing but a set of you can say a spreadsheet in which we will have rows and columns, and each unit or each number represents something. And for example, let's say here, remember, the thing you need to remember is that some cells might be empty. For example, let's say this movie 2, user 2 has not seen the second movie. So if he does like did not see the movie, then he will not give the rating. So my matrix will be empty as well, like 8, 7, 6, 9, blank, 5, 3, 8, 9. Some information of the given matrix can be empty as well. It is okay to be empty. Okay, so this is the definition of matrix. Now the next concept, the next definition we need to understand is that decomposition. To understand SVD, decomposition is the most important thing. So decomposition, right? Composition. So decomposition is nothing but breaking down a given matrix, a given matrix into simple form, right? And this is known as decomposition. Breaking down a like complex matrix into smaller pieces is known as simple form slash pieces is known as decomposition. And why is this important? Why do we do that? Let me tell you this, that uh, if you take a big matrix and break it down into different pieces, piece 1, piece 2, piece 3, this pieces gives us the structure, right? Gives us the structure which A can't give on its own, and from this structure we can extract patterns. Okay, so initially we are going with definitions, so this might like feel a bit slow, bear with me, but once we go as we go along in the session, everything is going to be crystal clear. So here what we are doing is that we are trying to understand each and everything. First of all, we have understood the definition of matrix. Now decomposition is nothing but, let's say you have a huge matrix. What you will do is that you break it down into pieces, and these pieces are important. Why they are important? Because the pieces has some structure, and the structure gives us something that the original matrix can't give. And from this structure, we can extract patterns. I'll tell you how exactly, but remember that this pieces, whatever the pieces are, piece 1, piece 2, piece 3, it can be a number of pieces. All these pieces are fundamental blocks, and this fundamental blocks gives us a structure, and these structures are important to draw patterns, and we cannot directly get this structures, this fundamental things from A, because A is a combination of P1, P2, P3. Okay, now if I multiply P1, P2, P3, if I multiply this thing, then I should get back A. If this thing is happening, then this is known as decomposition of a matrix. So the definition of decomposition is that you have a matrix, you break it down into pieces, and when you multiply all these pieces, you should get back the original matrix. When these two steps are happening, breaking down and coming back by multiplying, when this thing is satisfied, then we call this as decomposition of the given matrix. Now, if I have to tell you in simple number terms, then let's say I have 12, right? I'm taking a random number, 12. So 12 can be represented in the form of 3 cross 4. So these are like fundamental blocks of 12. 12 in itself is a big number, and this big number is broken down into smaller ones, and when you multiply the smaller numbers, you are getting original number. Similarly, when you have a matrix A and you are breaking down into different pieces like P1, P2, P3 up to Pn, and when you multiply it, you should get the matrix A back. When this thing is happening, then we call this as decomposition of the matrix. And the thing you should remember is that this gives first point a structure. The pieces, whatever the pieces we have, right? The pieces reveals something that original matrix can't. Second, second thing is that the computation becomes smaller. Computation becomes easier. Okay, these are the two things we should keep in mind when we talk about decomposition. First, it reveals something that A can't directly reveal. A is a complex matrix, that's why it can't directly reveal. Number two, the computation becomes easier. Here you can see the example that 12 is a big number. If you want to do anything by 12, let's say I'm multiplying 12 with something, it will give me a big number. It means big computation. But if I do something with their pieces, 3 and 4, they are eventually smaller numbers. Sorry, they are eventually smaller numbers, so I can do computation easily with it because it's smaller. Okay, got it. Now let's talk about SVD. So in SVD, we break the matrix, we break the given matrix into three pieces. So here also we do decomposition, but SVD is a special type of decomposition where we break our matrix into three pieces, piece 1, piece 2, piece 3, and uh, into three pieces, and we represent this pieces as the given matrix, let's say is A, then the pieces would be U multiplied by sigma multiplied by V of t. This is the definition of single value decomposition. I hope you have understood what is SVD. I'll go into numericals. Once we go into numericals, everything will become clear. But this is the definition of SVD. I hope you have got it. I have just mentioned what is decomposition. What is SVD? SVD is a special type of decomposition where we where we try to break our matrix into three exact pieces, exactly three pieces, and these three pieces are important, and I will talk about in few minutes. I will talk about like what are these three pieces, what are these pieces, and why do we need these pieces? I know you might have the doubts. Why do we need these three pieces, and what exact patterns we get from it? I will answer all this question as we move along, but remember, this is the main definition of SVD. Now, let's talk about why do we need it? Why do we need SVD in the first place? Okay, so to understand from where the SVD has emerged and why do we need it in the first place, we need to go back to our PCA, right? PCA and our eigen decomposition. So in PCA, let me write eigen decomposition. In PCA, if you remember what we used to do, first of all, we take the matrix, we take all the points along with it, along with its features, right? After taking it, what we do is first and foremost thing is calculate the covariance matrix, and after calculating the covariance matrix, this will be our A, right? After calculating covariance matrix, what we used to do is that we used to find eigen decomposition. Eigen decomposition is nothing but eigenvectors and eigenvalues. So we used to find eigenvectors and eigenvalues for the given matrix A, and from this we will get whatever the vectors we get, let's say v1, v2, v3, all these eigenvectors, and lambda 1, lambda 2, lambda 3. So here this v1, v2, v3 used to become our PCA lines, PCA1, PCA2, and PCA3. This is what we used to do. Okay, now if you remember this entire concept, let me draw with a different thing. This entire concept has a limitation. They require something, and the requirement for PCA to work is the requirement of PCA is that, first one, tell me the definition of eigen decomposition. The definition, or you can say the equation of eigen decomposition, is A V is equals to lambda V. This is the equation of eigen decomposition. But if you remember, in eigenvectors and eigenvalues, this equation came from square matrix. From square matrix. So my question is, what happens if if we get a non-square matrix? If we get a non-square matrix, then will this definition holds? The answer is no. The eigen decomposition will not work, because the eigen decomposition requires two things. One is it requires a square matrix. The second thing is, if you see this covariance matrix, the covariance matrix is symmetric in nature. Symmetric in nature. So in order to find the eigenvalues and eigenvectors and eigenvalues, these are the two things you need. What is the first condition? It needs to be a square matrix and it has to be symmetric in nature. Okay, and without this, if you, let's imagine a case where the matrix you have is a non-square matrix. If you don't have non-square, if you have a non-square matrix in the first place, then you cannot find eigen decomposition. When you can't find eigen decomposition, there will be no eigenvector and eigenvalues, right? When there are no eigenvectors and eigenvalues, then you cannot get PCA lines. Okay, and once you don't have PCA lines, then you cannot tell what is the pattern associated with that n-dimensional space. So the question we should ask, like, is that now is, did we failed, right? If the given matrix is a non-square matrix, then will PCA work for that? The answer is no, because PCA is built on top of eigenvectors, and eigenvectors require square and symmetric matrices. Now, what should we do? Because we have to find patterns. Even though the matrix is a non-square matrix, we have to find patterns. How are we going to do that? This exact same question is answered by SVD. You know what SVD will do? SVD tries to ask a question that, can we find, okay, we have non-square matrices. It means we have rectangular matrices. For non-square matrices, yes, we cannot, this part will not work. The normal eigen decomposition will not work. Now, can we, the question we should ask is, can we find something like directions? Something like, instead of taking directions, I'll write something like eigenvectors and values. Like, it's not, it doesn't have to be exactly same. For square matrix we get eigenvectors and eigenvalues, but for non-square matrix, can we get something similar to eigenvectors and eigenvalues? That is the question SVD asks, and the answer is yes. You can find something similar to eigenvectors and eigenvalues, and that something similar is singular value decomposition. That something is this: A is equals to U cross sigma cross VT. Okay, so I hope you have understood that why do we need SVD, because the concept of eigen decomposition is built on square matrices, and in real world cases, I can take an example in front of you right away. Let's say I'm taking a Netflix rating table. We took this table, right? So I'm taking the same thing. I'm taking an example with larger scale. So let me show you here. Okay, just imagine that I have a Netflix matrix, and in Netflix matrix, I have 20,000 users, right? And 50,000 movies. So how many points I have? I have total number of points, total number of units, like cells are 20,000 into 50,000. So this will be 4, 4, 4. So 10 into 10 to the power of 8 cells we have. So here you can see this is a rectangular matrix. And if we try to extract patterns from PCA, then yes, PCA might work, but it will be a lot of computation. I will show you, I will, for this matrix, when we talk about code, right, I will show you the comparison of when we implement SVD for a matrix. For this type of matrix, if we try to extract patterns from SVD and PCA, I will show you the difference. But remember, this is a rectangular matrix. And when it is rectangle, what it is telling me, it is non-square, and it might be or might not be a symmetric matrix. So if these two conditions are not getting satisfied, then how can you find eigenvectors and eigenvalues? Because eigenvectors and eigenvalues are built for square matrices. Okay, so this is an example. This is a practical example, a rectangular matrix, and for rectangular matrix, you cannot find eigen decomposition. That's why we use SVD. Okay, got it. Now, I hope you have got the idea of why do we need SVD and what is SVD. SVD is nothing but breaking down the given matrix into three fundamental pieces, and these three fundamental pieces are important, and each piece represents something. I'll tell you what it represents and how it represents and all, but the definition is breaking down the given matrix into three fundamental parts, and these three fundamental parts are important. Simple definition. And why we need it? Because there is a flaw in eigendecomposition that it only works for square matrices, and in real world we always don't have a case where we have square matrices. We might have non-square matrices as well. So in that case, what are we gonna do? In that case, we're gonna use SVD. Now, how are we gonna use SVD? Here's the third question. How are we going to use it? So let's talk about how. We have talked about what, why, and finally how we are going to use SVD. Okay. I want you to remember the equation. A is equals to U cross sigma cross V of t. Note it down in your notebook or wherever you want. Okay, so to find SVD, we are going to do a set of procedure, and along with it I'll take a numerical such that it will be easy to understand, right? It will be easy to, instead of talking ABC, numbers are easy to understand. So the first step is we have rectangular matrix, which is A. A is a rectangular matrix. Okay, for this rectangular matrix, can we turn a non-square matrix into a, can we convert the form of rectangular matrix, which is a non-square matrix, into a square matrix? Can we do that? That is the question we should ask. Or let's imagine this, like we have a rectangular matrix, right? Can we do something with this matrix? And when we do something to this matrix, I should get a square matrix. Can I do that? Is there a way to do it? Remember, there is a concept. Here comes the concept called as transpose. So what is transpose? Transpose is nothing but converting rows into columns and columns into rows, right? So here, how do we represent transpose? If we have A as a matrix, then A of t will be the transpose of the given matrix. Now there is a property. I believe in lecture 2, when we talked about inverses, we studied transposes, and in transposes, I believe, like if I remember, in symmetric matrices and transposes, between these two concepts, I told you a rule that if you have a rectangular matrix, right, if A is a non-square matrix, then AT will give you a square and symmetric matrix. This is the property which we are going to use. That if A is a non-square matrix, then AAT will give a square and the matrix will be symmetric as well. So what is the problem we had on the above case? That eigendecomposition only works for square and symmetric matrix. So even though A is a non-square matrix, then A cross AT, whatever the matrix we get, for example, let's say C is equals to A cross AT. So this matrix, this matrix is a very special matrix because it is square in nature and it is symmetric as well. And my question is, okay, you cannot find eigendecomposition for A, but can you find, uh, eigendecomposition for C? That is my question. Can we find it? We know that when you multiply AAT, you're getting square, you're getting symmetric. So when we get when a matrix is square and symmetric, can we find the eigendecomposition for that? The answer is yes. You can find eigendecomposition. So let me quickly do a numerical. Let's say I have A, right? I have an example actually in my book. Let me take it. Yeah, 1 0 0 1 1 1. So if you take this matrix, then AT would be 1 0 1 0 1 1. Now the product C would be multiply AT, right? So here AT A is equals to C, right? So here just write 1 0 1 0 1 1 multiplied by 1 0 0 1 1 1. Can you give me C? Can you tell me matrix C? So C would be let me find it. I don't wanna do manual calculation. So can you find a product quickly and tell me for this matrix what is the answer? I'll also take a screenshot and give it to GPT. Let me just do all the calculations with GPT, okay? So we have the matrix here. Tell me product, tell me answer. I don't want to do calculations. You can do calculations and all, but it's easy to directly give it to GPT. So here C would be okay, C would be 2 1 1 2. I hope it is correct. 2 1 1 2. Can you cross verify it once? So the answer would be 2 1 1 2. So here, if you see, I got a square matrix. This is a square matrix and symmetric as well. What is the definition of symmetry? The condition for symmetry is that C of t should be C as well. So if you find the transpose, here CT is equals to C of transpose is equals to 2 1 1 2. So here the condition is satisfied. So first of all, what we do is that we take the value of C. That is our first thing. We take a rectangular matrix and we'll try to get, like, from this matrix, can we get a square matrix? Yes, we can get a square matrix by multiplying with a transpose. And when you multiply with the transpose, you will get C. Okay, now the step two is that find eigendecomposition for C. That's what we do here. Eigendecomposition for C now. So here we have C, the value of C is equals to 2 1 1 2. Okay, now what is the equation tells us? Like C multiplied by V is equals to lambda V, right? If you take this here, then C lambda V minus lambda IV is equals to 0. And from this you can write C minus lambda I multiplied by V is equals to 0, and we know the value of C. And from this definition, from the definition of eigendecomposition, we can tell that determinant of C minus lambda I will be 0. Just try to put the values now quickly. Let's do the numerical. 2 1 1 2 minus lambda 0 0 lambda. Okay, it will give you 2 minus lambda 1 1 and 2 minus lambda. Okay, and the determinant of this would be 0. So if you try to calculate the determinant, you will get 2 minus lambda square minus 1 square, minus or plus, whatever. is equals to 0. So you will get lambda 2 minus lambda into 2 minus lambda. Is it plus or minus? Please tell me. Minus 1 is equals to 0. So 4 minus 2 lambda minus 2 lambda plus lambda square is minus 1. Minus 1 is equals to 0, and from this you can get minus 4 lambda plus lambda square plus 3 is equals to 0. So is it plus or minus? Quickly tell me. So lambda square minus 4 lambda plus 3 is equals to 0, and lambda is equals to minus b plus or minus root b square minus 4ac divided by 2a. We are trying to find the values of v, because okay, I'll tell you why. Because it gives us one of the pieces of SVD. So if you put it here, okay, if you put the values here, you will get um 4 plus or minus root 4 square 16 minus 4 into 1 into 3. So we will give 2 into 1. So we'll give 4 plus or minus root 16 minus 12 divided by 2. It will be 4 plus or minus 16 minus 12 would be what? 4. 4 divided by 2. Oh god. So lambda is equals to AZ. Wait, 4, right? I'll get 2. Okay. So 4 plus 2 divided by 2, and lambda is equals to 4 minus 2 divided by 2. So I'll get lambda 1 is equals to 8 divided by 2 as 4, and lambda 2 is equals to 2 divided by 2. So it will give me 1. I got two lambda values. Now if you try to put it here, the equation is c minus lambda I multiplied by v is equals to 0. And when you put the values of here, you will get the answer, right? The values 2 1 1 2 multiplied by, I hope I'm doing calculation here, it will give me 6, right? 6 divided by 2 is equals to 3. 2, yeah, 2 say 2 3 are 6, yeah, not, it will give me 3, not 4. Okay, so minus 3001 multiplied by xy is equals to 0. So when you do that, here we have two vectors, not xy, v1 v2. So v1 v2. So when you do that, you will realize 2 minus 3 1 1 2 minus 1. So it will give you a matrix of what, minus 1 1 1 0 multiplied by v is equals to 0. And let's give it to GPT now, because it will give you the values of v. We'll get two v's. Okay, so I'll just quickly take a screenshot, and before that is equals to 0. Okay, let's give it here. Give me two vectors, v1 comma v2 for the equation. So you will get your v now. What happened to it? Or else let's calculate manually, right? So uh, here this is in the form of a b is equals to 0. So if you try to put the values, just multiply with vector, you will get the answer. Let's wait. Why this is stuck? We're getting 0 comma 0 as eigenvector. It should not be the case. I think it is plus, not minus here. We have taken minus, it should be plus. I don't know. Let's see. So 3 comma 1, 1 comma 1, and yep, yep. So here, yeah, yeah, v1 is equals to 1 comma 1 and v2 is equals to 1 comma minus 1. Okay, so you got the matrix as v1 is equals to 1 comma 1 and v2 is equals to 1 comma minus 1. So you got the matrix. I hope it is correct. Let's see. Yeah, so we got the matrix now. So this matrix V, you will put it in column 1, column 2, which is our matrix V is equals to 1 1 and 1 minus 1. So this is a important matrix because we got one piece from the given equation. The equation is A is equals to U cross sigma cross VT. So we got VT piece from here. So to find vector like eigenvector V, what we do is that we take a non-rectangular matrix, multiply AT, you will get C, and find the eigenvectors of C. So it will give you one of the piece of SVD. Right, you got one piece. Now the next step is that after getting one piece, we are going to find sigma now. To find sigma, the definition of singular sigma is known as sigma, or you can represent this as well. The definition of sigma is that the singular value, the singular value, which is also known as sigma or small sigma, whatever it is the square root of eigenvalue. Eigenvalue. And remember that like the formula for sigma is root of lambda. This is the like formula for finding sigma. Now what we do is that after calculating here, we have the values are what are eigenvalues, 3 comma 2, right? 3 comma eigenvalues are 3 comma 1. Okay, so here we'll get two sigmas. So sigma 1 would be sigma 1 is equals to lambda 1 and sigma 2 would be root of lambda 2. So it will give me sigma 1 is equals to root of 3, sigma 2 is equals to root of 1. So root 3, value of root 3, value of root 3. 1.73. Okay, so it will be 1.73. So 1.73 is our sigma 1 and my sigma 2 would be 1. And our bigger sigma, the capital sigma, is the matrix that we get from this values, like sigma 1 0 0 0 0 up to 0 0 sigma 2 up to n. If they are n elements, right, then it will be like this, sigma n. So this will be our singular value matrix. Okay, and what it represents, it represents the, I'll tell you what it represents, but if you draw the values we get, right, so our value would be 1.73001. And remember, always sort the sigma values in descending order, because the sigma represents the common pattern that the given data has. In PCA, right, we had lambda 1, lambda 2, lambda 3, and we took the eigenvector which has the highest lambda value because it is the most important line. It represents the most useful information. Similarly, always take the sigma, always build the matrix in such a way that the sigma, or like a sigma 1 should be the highest, sigma 2 should be the second highest, because it represents the useful pattern that you need, and this represents the least useful information, and this represents the highest order of information. So sigma represents, singular value represents the patterns and the association of the patterns that you get, like what is the relation between movies and users, users and movies and all, and how important that relation is. The higher the value of sigma is, the higher the like importance of that relation is to you. So we got second piece now. This is the second piece. Up from our equation u cross sigma cross vt, we got v. We got v, and from v we can easily get vt. Vt is nothing but 1 1 and 1 minus 1. Right, as simple as that. So we get vt, we got vt, we got sigma. Now the last piece is u. So to find u, the last piece is u, right? So to find u, there is a direct formula that u of I is equals to 1 divided by sigma I a v I. So if you put the values directly, then you can get the, and whatever the matrix you get, right? So our u would be equals to u of 1, u of 2, and up to u of n. So this is the formula for finding the matrix u in singular value decomposition. Now, the thing is that if you solve the numerical as well, so u of 1 would be 1 divided by sigma 1 a v1. So it will give you, what is a? A is our matrix. Where is our matrix? This is our matrix. So take this matrix 1 0 1 1 0 1 1 1. So 1 divided by 1.73 multiplied by a matrix 1 0 0 1 1 1 multiplied by 1 1 1 minus 1. When you multiply it, you will get u1. Okay, let's see what is u1, and similarly u2 as well. So u2 is equals to 1 divided by sigma 2 multiplied by a multiplied by v2. So it will give you 1 divided by 1 multiplied by 1 0 0 1 1 1 multiplied by 1 here we got v1, right? V1 is, sorry, here we should take only v1. So let me erase this. Okay, because v1 is this, v2 is this. Okay, so here 1 minus 1. So let's see what is u1 u2. So u2 is equals to, so let's find uh, u1 and u2. Give me u1 and u2. You can do calculations. It's a lot of multiplication and stuff, so I don't want to do that. So we got u1 and u2 as this. As you can see, it's a big calculation in itself. So u1 is equals to 1 divided by root 6 112. So it will be 1 by root 6 1 by root 6, or let's write it in common form, 1 divided by root 6 112. Okay, sorry, I'm writing it in here. So 1 divided by root 6 112, and similarly 1 divided by root 2 multiplied by 1 minus 1 1 minus 1 0. So here, from here we got our matrix u is equal to u1 u2. So this will give us 1 by root 6 comma 1 by root 6 divided by 2 by root 6 and 1 by root 2 minus 1 by root 2 and 0. So this is our U matrix. So the point I'm trying to make here is that we found the third piece as well. From here, U cross sigma cross VT, right? So if you put back, we got our like a singular value SVD decomposition, right? A is equals to U cross sigma cross VT. So try to put the values 1 by root 6, 1 by root 2, 1 by root 6, minus 1 by root 2, and 1 by root 6, 0. Multiply it with our matrix. Our matrix is the sigma is, where is sigma? So yeah, multiply it with 1.73001 and multiply it with VT, which is 111 minus 1. So you will get the answer, which is equals to 100111 as A. Like this, we calculate the singular value decomposition. Now let's talk about like what is the meaning of it. Now we know how to calculate, how to get values and all. We know the formulas as well. The formulas to remember is, let me write the formulas. The main formula is A is equals to U cross sigma cross VT, right? And we this is a non-square matrix. It can be any matrix, like it can be square, non-square. Singular SVD works for any matrix, unlike eigendecomposition only works for square matrix. A works for everything, like SVD works for everything. Now this is first formula to remember, and second is that AT will give you square and symmetric matrix, and we consider AAT is equals to C, and from this you get V, and from V you will get VT, and from this also you will get lambda. Okay, now the third equation is that for our sigmas, for our singular values, the formula is that the value of sigma 1 is equals to root of lambda 1, like root of a square eigenvalue, right? Square root of eigenvalue. Similarly, right, lambda 2, and if there are n lambdas, then it will be lambda n. That is how we get all the smaller singular values. Now what we do is that we put it in a matrix, lambda 1 up to 0 0 lambda 2, like this. Like this we put everything in the given matrix. Like this we get sigma, we got V. Now the fourth piece is this, U of I is equals to 1 by sigma I A VI. From this you will get U as U1, U2 up to UN. So these are the formulas. This is how we find eigen decomposition. Now let's talk about what each piece represents. We know what it is, why we use it, and how do we find it. Now the last topic of the session is, we have our equation. Our equation is A is equals to U cross sigma cross VT. Okay, and what I think this is topic 5, what each piece represents and how do we draw patterns from it, right? What each piece represents. So let me write it here, that V, which is V of t, right? You can take V of t. Both are almost same, as you can see in the example. V of t is the right singular matrix, right? It is right, it is on the right side, right singular matrix, and it represents the pattern of columns, pattern of columns with respect to rows. For example, in our case, right? We have movies. So we will try, movies are our columns. So this will tell how movies are changing, or what are the same movies that users are liking. Users are liking. So this will create the cluster of movies, like the similar movies liked by users. So here everything will be about columns, which is movies in our case. So we'll tell like what movies are liked by users and why they are liking this. What is the pattern? What are the types of users who are liking Avengers movies? What are the type of users who are liking Batman movies? Like that you tell. So everything is related to movies, columns, right? Now U is the left singular decomposition, right? Left singular decomposition, and it tells you the patterns about rows, patterns of rows, like what are the categories of users who are liking one particular film, right? We talk about users now, so talk about with respect to columns. So here we talk about users, like what are the types of users who are liking one particular film, right? Or one category of film, sci-fi, romantic, whatever, right? So it tells you about column, V tells you about column, U tells you about a row, and sigma tells the weightage of each group. Okay, so this is about it. This is why we use eigenvalue decomposition, right? Sigma tells you like let's say there how many people are there uh, for sci-fi. There might be more number of people for sci-fi than romantic movies. It tells you that like what is the weightage of each group, how many number of clusters, how many number of points are there, and the highest point, the cluster which is having highest point will have the highest weightage. So it tells you that. So this is what it is. Now if I come back to all the way up, I have written few questions like yeah, where is it? What are these points? What are this V? So U is about rows, sigma is about weightage, V is about the patterns of columns. And why do we need it? So from this, we draw a graph, and that graph will tell what are the different types of clusters you can extract, the pattern you can extract. So this is about SVD, and I want to talk about one more topic before we end the session. Let me come back to our example. Okay, where is our example? Real world example. Somewhere I have written. Where is it? Yep, this one. So here you can see that how many users are there? 20,000 users. Okay, and how many movies are there? 15,000 movies. Okay, my question is, can I, sorry, can I implement, okay, again, implement PCA? Okay. Uh, to answer this question, in our previous example, when we talked about PCA, I have taken Mises and Jean's student marks, right? So if you take the student marks, I have math, I have physics, I have like two subjects, for example, and student one, student two, student three. So if you take, this is also a rectangular matrix. If you see here, each point, each point is having two features. And if you draw the matrix, it is a 3 cross 2 matrix. Here, this is a 20,000 cross 50,000 matrix. Okay, so can I implement PCA? The answer is yes, you can implement PCA if you assume that each user has a point. Let's say user 1 has a point and he's having 50,000 features, M1, M2, movie 1, movie 2. Each movie is a individual feature in itself, right? And if you consider this, then you will end up having 20,000 points, and each point is having movie 1, movie 2, movie 3 values, okay, up to movie 50,000. Okay, now the problem is you can implement perfectly PCA here, but the problem is, first let me tell you, observe the covariance matrix. Covariance matrix is a n cross n matrix, and for this, because they are 50,000 features, we will get a matrix of 50,000 into 50,000 cells. So it will be 25 into 1 times 100, 100, whatever, like 4, 10 to the power of 8. So it is around 28 million, or 25 250 million operations if you see here. So here we will have 250 million cells. So that's a lots of computation. Lots of computation. And we are, number two is that we are telling only about users. Right here, if I am drawing the PCA for this, I'll be telling what are the students, what are the categories of students. Similarly, here I can tell what are the categories, of users, right? Categories of users. I will be only talking about users only, right? I'll say only about users. I cannot talk about movies. That is one-sidedness. PCA tells you one-sided data. It can tell you about only students, only users. But here we are, let me come all the way back. So first of all, U is telling about users. So what are the pattern you get from PCA, right? Pattern from PCA, it is the same pattern. So U is telling about that pattern. And also it is giving me another pattern, and that pattern is movies pattern. So if I consider movies as individual points and users as features, then I'll get PCA graph for movies. So again, like if I have to find for movies, then again I have to do all the operations here. Let me come back. Where is my, I think it's up. Yeah. So here, if I consider users as features, movies as points, then I will get 20,000 cross 20,000 covariance matrix, and it tells about movies, like how movies are behaving and all with respect to users. This tells about how users are behaving with respect to movies. So these are two different implementations. I have to do two different implementation to tell about users and about movies. So 25 to the power of 8 computation and 4 into 10 to the power of 8 computation. This many computations I have to do in BCA to calculate the two sides of the coin. But in SVD, with one single implementation with very minimum computations, you can tell the pattern right away, the two sides of the coin right away, about movies with respect to users, about users with respect to movies, and the importance of each curve. So this is about singular value decomposition, complete theory. We have talked about what is it, why is it, how do we find it, and what each piece represents. We have talked about it, and how efficient it is with respect to PCA. So this is the theory. I hope you got the overall understanding. I tried to break it down into very simple pieces. If you try to go on internet, read it by yourself, you'll find very complex language. I tried to break it down into very simple language such that anybody who is watching or listening can understand. Okay, so this is the theory. In the next class, which is around 1 or 2 hours later, we will see implementation of PCA. We will build a recommendation system for users based on their liking. You will tell, like for example, I'll tell you the problem statement that let's say I have Avengers movie, Christopher Nolan movies, and romantic movies, and I have user 1, user 2, user 3. So let's say user 1 has seen Avengers, has seen Christopher Nolan movies, but he has not seen romantic movies. And other users as well, you have rating. Now you will decide from your recommendation system that whether he will like romantic movies or not. And if he likes, then you will show the romantic movie recommendation, or else you will not show. And how can we tell whether he will like or not? From the concept of SVD, we extract patterns and we give custom rating here. And if the rating is high, we'll show the movie. So I'll talk about it when we implement the code. I will talk about the problem statement in detail, but I hope you have understood the overall concept of SVD. So let me stop my screen share. If you have listened till here, then thank you so much for watching. So thank you everyone. Thank you for watching this entire 1 hour theory class. And in the next class, which is on Build Sunday, I think it's episode 6, we will build SVD from scratch and we will build a Netflix recommendation system. We will code that together. So it's going to be really interesting and I'm really excited to see you there. So with that being said, thank you for watching. And if you have any doubts, please feel free to comment down or DM. I'll be more than happy to answer you guys. So thank you for watching. I'll see you on Build Sunday.